Have you ever looked up at the night sky? I mean, really looked. Far away from the city lights, where the Milky Way spills across the darkness like a celestial river. Each point of light is a sun, a star, and many of those stars have planets of their own. This isn't science fiction. This is the universe we live in. The urge to go there, to see what's out there, is deeply human. It's the same impulse that pushed our ancestors out of Africa, across continents, and over vast oceans. We are explorers. It's encoded in our DNA. The cosmos is simply the next and final frontier. This cosmic dream isn't just about adventure, it's about survival. Our sun won't burn forever. Our planet faces challenges, some of our own making. Spreading out among the stars is the ultimate insurance policy for the human species. It's a way to ensure that all our art, our science, our history, everything that makes us who we are, doesn't just vanish if something goes wrong here at home. We look to the stars not just with curiosity, but with a sense of profound responsibility for the future of our species. The universe is calling, and it would be a shame not to answer. Think about it. Every culture throughout history has told stories about the stars. Let's talk numbers. Big numbers, the kind that break your brain a little. The closest star to our sun is Proxima Centauri. It's only about 4.2 light-years away. A light-year is the distance light travels in 1 year. Light is the fastest thing in the universe, 186,000 miles per second, nearly 671 million miles per hour. So Proxima Centauri is about 25 trillion miles away. That's a 25 followed by 12 zeros. If you tried to drive there in your car at highway speeds, it would take you about 45 million years. And that's our nearest neighbor. To really grasp this, let's shrink the universe down. Imagine our sun is the size of a grapefruit in New York City. On this scale, Earth would be a grain of sand orbiting about 50 feet away. The farthest planet, Neptune, would be another grain of sand about 30 blocks away. And where would Proxima Centauri be? It would be another grapefruit in San Francisco. Between these two grapefruits lies a vast, cold, and almost entirely empty space. Our entire solar system, which seems so huge to us, is just a tiny, isolated neighborhood in a cosmic city of unimaginable scale. This isn't a barrier, it's a filter. It ensures that only the most determined and ingenious species get to leave their cradle. So, how fast can we go right now? Our fastest spaceships are impressive by human standards, but on a cosmic scale, they are embarrassingly slow. Take the Parker Solar Probe. It's one of the fastest objects ever built by humanity. Whipping around the sun, it has reached speeds of over 430,000 miles per hour. That's fast enough to get you from New York to Los Angeles in about 20 seconds. It sounds incredible, right? But even at that blistering pace, it would take the Parker Solar Probe about 6,600 years to reach Proxima Centauri, our nearest stellar neighbor. Let's put that in perspective with a more traditional spacecraft. The Voyager 1 probe, launched in 1977, is currently hurtling through interstellar space. It's traveling at about 38,000 miles per hour. After more than 4 decades of travel, it has left our solar system, a monumental achievement. But its journey to Proxima Centauri, if it were pointed in the right direction, would take about 75,000 years. We're not just slow, we're glacially, cosmically, profoundly slow. Our rockets are simply not up to the task. The problem is one of fundamental physics. Our current rockets work by throwing mass out the back to push themselves forward. This is Newton's third law. For every action, there is an equal and opposite reaction. But to go faster, you need to throw more mass or throw it faster. This requires more fuel. But carrying more fuel makes your ship heavier, which means you need even more fuel just to push the extra fuel. It's a vicious cycle known as the tyranny of the rocket equation. It's why our spacecraft are mostly fuel tanks with a tiny little probe tacked on top. So if rockets won't work, what will? One of the most elegant and scientifically plausible ideas is the light sail. Imagine a sailboat on the ocean. It doesn't carry its own engine. It uses the wind to push it forward. A light sail works on a similar principle, but instead of wind, it uses light. Yes, light. Light is made of particles called photons. They have no mass. They do have momentum. When a photon bounces off a reflective surface, it gives that surface a tiny, tiny push. It's an almost imperceptibly small force, but in the vacuum of space with no friction, those tiny pushes can add up. You unfurl a massive sail in space, ultra-thin and highly reflective. This sail could be hundreds of miles across, thinner than a piece of plastic wrap. Shine a powerful laser beam on it from Earth, or from an orbiting station. The relentless pressure from the laser photons would push the sail, and the small probe attached to it, faster and faster. No heavy fuel to carry. Escape the tyranny of the rocket equation. Gentle at first, constant over time. Over days and weeks, the spacecraft accelerates to incredible speeds. Studies like Breakthrough Starshot suggest a wafer-sized probe could reach about 20% the speed of light. Journey to Proxima Centauri, just over 20 years, not 75,000, transforms interstellar travel into something achievable within a human lifetime. Send a swarm of tiny nanocraft to our nearest star, and the people who launch them could still be alive to see the pictures they send back. Now let's get a little more speculative. What if, instead of trying to travel through space, we could travel with space? This is the core idea behind the warp drive, made famous by Star Trek. It's not about moving your ship at impossible speeds. It's about manipulating the fabric of space-time itself. According to Einstein's general relativity, massive objects curve space-time, and that curvature is what we experience as gravity. The warp drive proposes to do this on purpose, creating a bubble of space-time around the ship. The concept, first formulated by Miguel Alcubierre in 1994, involves expanding the fabric of space behind the ship and contracting the space in front of it. Imagine you're a surfer on an ocean wave. You're carried along by the wave. The warp drive would make a similar wave in space-time. The ship inside the bubble would be essentially stationary relative to its local space. It's the surrounding space that's doing the moving. Crucially, this doesn't violate Einstein's speed limit. Nothing with mass moves through space faster than light, but the Alcubierre idea moves space-time itself, which has no known speed cap. In theory, that could let you cross the galaxy in weeks or days instead of millennia. The crew feels no huge acceleration or time dilation, just a calm ride. It's basically a cosmic cheat code. But there's a catch, a very big one. To create this space-time distortion, you would need a mind-boggling amount of energy. Let's come back to Earth for a moment, or at least to slower than light travel. What if a journey to the stars still takes hundreds or even thousands of years? How could a human crew possibly survive? One answer that has captivated sci-fi for decades is suspended animation cryosleep. The idea, put the crew into deep hibernation, slow metabolism to a near-complete stop. Bodies preserved at extremely low temperatures, halting aging, and the need for food, water, air. The ship becomes a robotic caretaker, guiding itself across the interstellar void, while passengers sleep the centuries away. As it approaches the destination, automated systems gently warm the crew, waking them to begin the mission. For the travelers, the journey feels instantaneous. Close eyes in our solar system open them, moments later from their perspective in orbit around a new star. Same age, but everyone and everything they knew on Earth is gone, turned to dust by centuries. True long-term human cryopreservation is still far beyond our grasp. We can freeze cells, but freezing and reviving a human without massive cellular damage is a monumental medical challenge, yet to be solved. There is a middle ground between the slow crawl of chemical rockets and the wild speculation of warp drives. That middle ground is fusion power. Our own sun is a giant fusion reactor. In its core, it smashes hydrogen atoms together to create helium, releasing a tremendous amount of energy in the process. This is the energy that warms our planet and makes life possible. A fusion rocket would aim to do the same thing, but on a much smaller scale, creating a tiny, contained star inside an engine to propel a spacecraft. A fusion rocket would be vastly more powerful and efficient than any chemical rocket. Instead of burning fuel, it would fuse light atomic nuclei, like isotopes of hydrogen called deuterium-tritium. The resulting high-energy particles would be directed out of a magnetic nozzle, generating enormous thrust. A fusion-powered ship could continuously accelerate for months or years, potentially reaching speeds of 10% the speed of light or more. One famous design concept from the 1970s was Project Daedalus. This was a serious engineering study by the British Interplanetary Society for a robotic probe to fly by Barnard's star, about 6 light-years away. The probe was designed to be a 2-stage fusion rocket. It would detonate tiny fusion pellets, like miniature hydrogen bombs, hundreds of times per second inside a magnetic confinement chamber. The main obstacle to building fusion rockets is that we haven't yet mastered fusion power here on Earth. Scientists around the world are working on projects like the ITER tokamak in France to create a sustained, controlled fusion reaction that produces more energy than it consumes. It's an incredibly difficult engineering challenge, often described as building a bottle for a star. Science fiction is more than just entertainment. It's the laboratory of the human imagination. It's where we test drive our futures. It's where we explore the consequences of new technologies. It's where we inspire new generations of scientists and engineers to turn fantasy into reality. The relationship between sci-fi and real science is a two-way street. Scientists get ideas from fiction. Writers base their stories on the cutting edge of scientific theory. Think about the communicators in Star Trek. They were a wild fantasy in the 1960s. Today you have a smartphone in your pocket that's thousands of times more powerful. Arthur C. Clarke proposed geostationary communication satellites. That idea now forms the backbone of our global information network. The stories we tell create a target for reality to aim for. They make the impossible seem inevitable, a cultural roadmap for technological progress. The warp drive, the light sail, the cryosleep pod, all staples of fiction long before serious scientific papers. This process of inspiration is vital. When a young student watches a movie about exploring distant galaxies, it plants a seed. That seed can grow into a passion for physics, engineering, astronomy. They might develop a new alloy for a light sail, or write the code for an autonomous starship's navigation system, or make a breakthrough in fusion energy. Science fiction provides the why, the grand aspirational goal. Science and engineering then get to work on the how, the nitty-gritty details. We're living in an age where the line between sci-fi and fact is increasingly blurred. Rovers on Mars sending back high-definition pictures, thousands of exoplanets discovered orbiting other stars, 3D printing rocket components, planning missions to mine asteroids. The dreams of yesterday's fiction are becoming today's engineering projects. The journey to the stars will begin in our stories. The path to the stars is long and it is paved with unanswered questions. We've talked about the engineering challenges, the engines, the materials, the energy sources. But there are deeper mysteries too. How do we protect a crew from decades of exposure to cosmic radiation? How do we build a closed-loop ecosystem that can support human life for centuries without any help from Earth? What are the psychological effects of being confined to a small metal box, knowing you can never go home? These are not just technical problems, they are biological and human problems. And then there's the biggest question of all, is anybody else out there? As we develop the capacity to travel between stars, we also increase our chances of finding an answer. Are we alone in the universe? The silence we've heard so far is profound. This is the Fermi paradox. If the universe is teeming with life, where is everybody? Perhaps civilizations are too far apart. Perhaps they destroy themselves before they can achieve interstellar travel. Or perhaps, just perhaps, they are out there waiting, and we are on the verge of developing the technology to finally say hello. The quest for interstellar travel is, in many ways, a quest to understand ourselves. It forces us to think on the longest possible timescales and to work together as a species. No single nation or corporation can build a starship alone. It will require a global effort, a pooling of resources and intellect on a scale humanity has never before attempted. In reaching for the stars, we might just find the best version of ourselves here on Earth. It's a goal that can unite us, giving us a common purpose that transcends our petty squabbles and short-term thinking. So the next time you look up at the night sky, don't just see points of light. See destinations. See possibilities. The universe has been waiting for 13.8 billion years. We are a young species, just waking up to the vastness of our cosmic home. The challenges are monumental, the distances are terrifying, and the timeline is long. But we are a species of dreamers, of builders, of explorers. The story of humanity is far from over. The best chapters are yet to be written, and they will be written out there in the silent, starry dark. The journey has already begun.